Hello everyone and welcome on today's video. My name is Wouter Pere, I'm the founder and main developer of GHEtool, and today we're going to continue our discussion on the hydraulic design of bore fields. So 2 weeks ago we introduced or talked about the concept of pressure drop and why it is important for your hydraulic design and for your bore field design in general. And in today's video I want to show you how GHEtool can help you with this task and how we can estimate the pump energy and what insights we can get from really taking a closer look at the hydraulics of your bore field. So let's dive into it. To recall the first part of this series, we said that the pressure drop can be calculated using this formula, where we have on the one hand a factor using taking into account the pipe length and the pipe diameter, which we called the major losses or the friction losses. And these are all the losses related to friction between the fluid and the pipe, and within the fluid itself, etc. And then we have another term, which is the summation of all the local friction factors, or the minor losses, which we can identify or point to in our hydraulic design. These are all the bends, all the T-junctions, etc. And this whole, or everything within the brackets, is multiplied by a factor taking into account the density of the fluids and the velocity squared. This has to do with the kinematic energy, if you want. If you have not watched our theoretical explanation of what a pressure drop is and why it's important, please watch this video or read the article, because it's important if you really want to understand the different concepts that we're going to talk about in this video. So this is basically the theoretical formula to calculate the pressure drop. Now, if we want to calculate the pressure drop across the whole bore field, which is important for a pump design and the estimation of the energy consumption of the circulation pump, it depends on quite a lot of parameters. For example, the way we route the horizontal pipes, if there are quite a lot of right angles, if we, let's say, just connect the boreholes directly to the collector, or we use series of parallel connections, it has an influence on how the flow behaves in the system and what the pressure drop of the bore field in fact is. We have the importance of the collector positioning, if we have sub-collectors or not. Perhaps we use different pipe diameters also, and this all has an effect on the pressure drop. And if we want to estimate the pressure drop of the bore fields, there is one general idea which is really important, and it's this assumption that actually makes it rather feasible to calculate this. And that's that we want to have the same flow rate through every borehole. And this is what's called, we want to have a hydraulically balanced system, meaning that every borehole has the same flow rate. Now, why is this important? Because we want to ensure that there is an identical heat transfer for every borehole inside of bore field. So we want to be able to extract or exchange the same amount of energy through every borehole of a bore field in order to have the most efficient system. Now, of course, this is a theoretical assumption because the boreholes in the middle of our bore field do not have the same potential of exchanging energy as the boreholes that are at the edge of our bore field due to the average temperatures, but that's a discussion for an all other video. So the main idea today is that we want to have an hydraulically balanced bore field where every borehole has the same flow rate. And the way we do that is that every borehole should have the same pressure drop. So this means that if you pump your fluids inside the main collector, there is no preference path the fluid will take, because all the paths have the same pressure drop and will take the same amount of effort to go through. So this is really the essential and central idea. So basically what we have to do is we simply have to find the worst case. So we have to find the borehole which from the hydraulic standpoint is the worst. So it's the furthest away from our main hydraulic collector. So what we do is we find that borehole, we calculate the length of the horizontal route to that collector, we calculate the pressure drop across the borehole including the horizontal connection, and then we know what the entire pressure drop of the whole bore field is. Because we want an hydraulically balanced system, we will make sure that all the other boreholes and horizontal connections have the same pressure drop. We will calibrate it that way using valves. And then we have the pressure drop across the whole bore field being the same as this worst case situation. So if you take a look at an example here, we have 14 boreholes and we have a building with a main collector. And we can see that the pressure drop of the boreholes really close to the building will be rather small, let's say, because the horizontal connections are small. It's 6 meters in this case. All the boreholes are 6 meters apart. But if we move further away, the route will be longer. The horizontal pressure drop will also be bigger. And you can see that the borehole, which is the furthest away, which is this borehole, it has a total horizontal length of 30 meters. And this will have the largest horizontal pressure drop. So if we calculate just the pressure drop across this borehole, being connected to the main collector, we know the pressure drop of our entire bore field, and we can go ahead and calculate the required pump power and the required or the estimated pump energy. So let's dive into GHEtool Cloud, and I'm going to show you how you can do it for yourself. So here we are in GHEtool Cloud. I created a new project and I already entered the borehole into GHEtool. This is the same configuration as before, as we saw in the PowerPoint. And I set the fluid properties to 25% of glycol with a flow rate of 0.3 liters per second per borehole. So now if we want to calculate the hydraulics, we go to the General tab and we say, well, we want to calculate the pressure drop of the bore field, and we set that the longest connection was this 30 meters. So let's go ahead and calculate that. And this is the result we end up with. So there is a new tab, or new section in the result tab, which is related to the hydraulic design. And here you can see the pressure drop across one borehole, which was already in the software. And now there is also the pressure drop of the entire bore field, which is 21 kilopascal. And the difference between both is related to this horizontal connection. And we see that for our design, we have 4.2 liters per second through our entire bore field, and we require 88 watts of pump power with an estimated pump energy consumption of 200 kilowatt hours per year. Now the way this pump energy is calculated is using the assumption of full load hours. So it will calculate based on your energy demands, how many hours the pump will run in full load. Now of course in a next update, and we're working really hard on this, we want to take into account modulating pumps and actually let this mass flow rate vary throughout the simulation. But this is a first estimate, let's say. And here below we have a very interesting graph, which is more or less quadratic as we saw earlier, but there are two jumps in it. So first let us see that this 4 liters per second is actually our design criteria. So it's the design, we designed the bore field with 4.2 liters per second, which is actually right in the middle of this figure. And the first jump you can see here, it's the transition between a laminar and a transient flow for our horizontal pipe. And that's also the reason why it's a rather small jump, is because the effect of the horizontal piping, it's only 30 meters in comparison to the 120 meters of our bore field. So that's why this jump is small. The larger jump here in the end has to do with our borehole itself becoming turbulent. So we have, as I can show you here, we have a double U-tube inside of borehole, and this will become turbulent when we have a flow rate of around 7 liters per second for the entire borefield. Now, if we look at the temperatures for a moment, we see that we cross the minimum average fluid temperature we set. So let's go ahead and duplicate this scenario, and let's play around with the hydraulics. So we saw that we have a total flow rate of 4.2 liters per second. Let's jump into the borehole resistance step, scroll down, and you see here that we can enter the flow rate per borehole or for the entire bore field. So I'm going to say now, well, we have this 4.2 liters per second for the entire bore field, but I'm now going to connect the boreholes in series. So I'm going to assume that we have 2 boreholes in series each time. And if we calculate our system now, what we will have is we will have the same flow rate through our system, the same 4.2 liters, but our borehole thermal resistance is way smaller due to the fact that we're now no longer laminar inside the borehole, but we're transient. And as you can see, we now touch the design criteria or the minimum average fluid temperature, which is exactly what we want. But on the other hand, the hydraulic design and the pressure drop change dramatically. So we have a way higher required pump power, we have a way higher estimated pump energy consumption, and also the difference between the pressure drop across one borehole and the entire bore field has changed dramatically due to the fact that we now have a bigger influence of the pressure drop across the horizontal pipe, because there the fluid is way more turbulent now. So what we can do, for example, is to say, well, let's duplicate this scenario again, make it scenario 3. Go back to the general tab, and let's say, well, instead of using a DN40, so a pipe of 40 millimeters, let's use a pipe of 50 millimeters, which has a wall thickness of 4.6, if I'm not mistaken. So let's calculate it again and see what the different results are. So as you can see, the pressure drop across one borehole is the same in both scenarios, but what is different is the pressure drop of the entire bore field. And that's because now we have a bigger pipe horizontally. The pressure drop there is decreased, and we have 50 watts of pumping power less and 130 kilowatt hours per year of electricity consumption. Also less due to this change in horizontal connections. So this might seem small for this field of only 14 boreholes, but what you should remember is that for bigger bore fields, up to 50 or even 100 or higher number of boreholes, this horizontal, or the contribution of the horizontal connections, can become really significant. And with this simple addition, you have a really powerful tool to play around and to see, well, what's my required pump power for my design I actually made. So here you can also immediately see if we just lower the flow rate a little bit, then we will end up with a more favorable hydraulic regime, a fluid regime where we require less pumping power, and we will also have less pump energy. But of course, you need to check that the temperature drop, or let's say the delta T across the evaporator of your heat pump, is typically also in the range of 3 to 5 degrees Celsius. So you cannot play too much with the flow rate because you have to make sure that all your other components work as well. But if you have a certain design that you made, you can now check, well, this is the required pump power I need, this is the pressure drop of my bore field, and you can also see if you connect them in another way or you change the length of the horizontal routing, what the effect will be on your hydraulic behavior of your system. So I hope this video was helpful. I hope you take into account the hydraulic design of your bore field as well. This is a feature we implemented for every bundle of GHEtool, from the essential design and the optimization bundle, because we believe it's really important that we start paying attention to this type of parameters related to the hydraulic design of bore fields. So if you think this is interesting, please consider subscribing to this channel. It really helps us share this message with more designers and drilling companies and engineering firms all across the globe. If you have an idea for an article, please let us know. We're more than happy to see if we can write something about that. And I hope I see you in the next video. Take care. Bye.